Okay, so we'll get started.
Oh, yeah. Thank you.
Okay, good afternoon, everyone, and welcome to our next installment of our CDAC webinar series coming to you from the University of Illinois in Chicago. Today, we're pleased to welcome Ding Pan. Ding is in the Department of Physics and the Department of Chemistry at the Hong Kong University of Science and Technology. Professor Ding obtained his bachelor's degree in physics at the University of Science and Technology of China in 2025 and his SCD at the Institute of Physics at the Chinese Academy of Sciences in 2011. During that time, he was a visiting researcher at the Fritz Haber Institute of the Max Planck Society in Berlin and a Thomas Young Center Junior Research Fellow at University College London. He worked as a postdoctoral researcher in the Department of Chemistry at UC Davis, and then also at the Pritzker School of Molecular Engineering at the University of Chicago, just down the street from us, before he joined his current position in 2016. His work has been recognized by a number of awards from international scientific organizations, including the Croucher Innovation Award in 2018, the Deep Carbon Observatory Emerging Leader Award in 2019, and the Excellent Young Scientist Award in 2020 from Hong Kong and Macau Natural Science Foundation of China. And also by his own university in the School of Science Research Award in 2022. Today, Professor Ding will talk about something we haven't really heard about in quite a while in our series, and that will be the development and application of first principles statistical mechanics methods for studying carbon, hydrogen, oxygen, nitrogen supercritical fluids. Welcome, Professor Ding.
Okay. Hi. I should say good afternoon. So first, I would like to thank Stephen for a very nice introduction. So can you hear me well, Stephen?
Yes, we can hear you.
Okay, great. Yeah. And also, I would like to thank Ross for inviting me here. And first, forgive me if I say something silly because now it's now it's 2 a.m. in Beijing. Okay, so here I'm very glad to show our research, recent research on this carbon-bearing supercritical fluids. And the first, we call method is first principles mechanics method. So what is that? So first principle, that means that we have to do the very good electronic structure calculations, usually at the density functional theory levels, to describe, for example, like the chemical bondings. And also at the same time, we also need to do some sampling, for example, like a canonic ensemble like this, so that we can have the finite temperature effect, we have the pressure effect, and also that we may also have some spatial confinement effect. And when we do this, and often we have to fight against some bias, for example, that this called a sampling bias. So that means that, okay, we hope that we are not stuck here, but also that we can sample, well, for example, from here, this valley to another valley here. So this is basically like the overall method we are talking about. And technically, that what we are doing, so most of part of my research is based on the AB initial molecular dynamics simulation, and also some method development. And in the electronic structure calculation part, that we use the density functional theory. So, for example, here we use the PBE and the PB0 functionals, and also with like the van was dispersion corrections. So we use a non-conserving pseudo-potential. And also that here, when we do samplings, usually like we do that MPT or NVT ensemble. And also for this kind of sampling bias, like in this work, we do the enhanced sampling. And for example, that here we use the adaptive biasing force method. So some of you probably heard like that metal dynamics, that is a biasing potential. So basically, you can understand that after we integrate the force, we get the potential. And here in our study, we found that this adaptive biasing force is very efficient for our purpose. Okay, so all of these are implemented in a free code, very efficient. It's called QBox, and also with the Sage code for this enhanced sampling part. And also that in the last part of my talk, we will also talk about some method beyond the enhanced sampling here. Okay, so, and also I would like to introduce some background of my research. And basically that the scientific problems is, I think, from this, I would say that it's a very, very nice international collaborations called Deep Carbon Observatories. And it's a global research programs to transform our understanding of Earth, of carbon in Earth, inside Earth. It's a pity that this collaborations has already finished, but there are like a lot of interesting questions still there. So, for example, that why we care the carbon inside Earth. So we all know that the carbon cycle is very important for sustainable development of human. But if you look at the Earth as a whole, in fact, more than 90% of the carbon is basically is buried inside the Earth. For example, here, like in the crust, in the mantle, or even in the core. And those deep Earth carbons is not isolated, but keep exchange carbons with the carbon reservoirs close to the Earth's surface, like here. So for example, during the exchange, like the carbon-bearing supercritical fluid plays a very important role. So in this program, there are many interesting questions like the formation of a diamond, abiogenic petroleum orange, and even orange of life. And okay, so in my research, in my talk today, basically, I would like to focus on these two topics, especially about the dissolved carbons in deep fluid. That deep fluid is containing that mainly water here. Okay, so let's start from this simple question here, okay? So when we dissolve carbon, like CO2 in water, what they are, okay? So for example, that in a color at ambient conditions, and when we dissolve CO2 into it, more than 99% of dissolved carbon, in fact, is molecular CO2. But how about when we go to the upper mental conditions, see that pressure up to 10 gigapascal shows some interesting and also complicated reactions inside here. So the question here is that what is the form of a dissolved carbon present at such high pressure and high temperature conditions, molecular CO2, bicarbonate ions or carbonate ions or some other species? Okay, so first I would like to introduce this work that's mainly done by my former postdoc, Laura. So now he's working as a postdoc in Germany. And basically, like we study that when we dissolve CO2 in water under these extreme conditions, and how about the chemical composition here? And this plot just shows that the more percent of some important carbon species as a function of initials, the CO2 concentration here. This is the x-axis is the mole fraction here. And you can see that there are some typical CO2 reaction here. And the interesting thing is that I would like to focus on this red curve. So this shows the more percent of carbonic acid. And you can see that carbonic acid at ambient conditions, normally we just ignore it because it's very, very rare. But now you can see here that at a certain concentrations, you can see that from this curve, the carbonic acid now becomes the most dominating carbon species in this solution. So that means that here, just to show you that for example, here in our research, we found that at this pressure and temperature range, that this carbonic acid is an important carbon carrier in the deep carbon cycle here. Okay, so this is the work about the solutions of CO2. So how about like how about the reduced carbon? So what we call the reduced carbon? Okay, here. And the CO2, you can consider that the carbon is fully oxidized. But from the geoscience, we know that with increasing depths, Earth's interiors becomes more and more reducing. So that means that we would expect to see more and more hydrocarbons. And here the hydrocarbons can be very important for many interesting things, like formation of diamonds, the orange of petroleums, or even the deep life here. Uh, yeah, so okay, here, right. And so in fact, as early as the 19th centuries, a famous chemist, Dmitry Mendeleev, just proposed that petroleums might be formed by some like abiogenic means. Okay, so now the question is that it's like this: if it's true, then how to form these higher hydrocarbons from the inorganic carbon here? Okay, so many geochemists suggest that maybe that this kind of organic carbons come from these famous reactions called Fischer-Tropsch synthesis. And okay, Fischer-Tropsch synthesis, in fact, is a very, very important reactions in chemical industry. But here that in deep earth, the things can be very different. And I will talk more later, I would say here. So here, normally we, in this talk, we just follow the geochemical convention. That is that we refer this Fischer-Tropsch type synthesis in general to converting inorganic carbons to organic metals, okay? And for example, that in these reactions, that the water-gas shift reaction is a key reaction to balance the CO and molecular hydrogens ratios here through this reaction here. Okay, so that's very interesting. That water-gas shift reaction basically that it will release heat. So that means that thermodynamically it's a favored reaction, but kinetically it's difficult. Why? Is because it has a very large reaction barrier. So in industry, usually they use the transition metal catalysis, for example, like this and this at above ambient conditions. But now the problem is that for those kind of industrial catalysis, that usually do not exist in deep earth. So then that if this kind of reaction can happen, then how they are, okay. Okay, so first here that we studied like this water gas shift reaction here, and we dissolve one CO molecules in water, and then sorry, and then we just conduct AIMD simulation here, and you can see that at these conditions, that this one CO after about 200 picoseconds, it dissolves and it becomes the formic acid. And also, if, for example, that if you increase the pressure from 10 gigapascal to 13 gigapascal, and then this reaction can be even faster here. And also the interesting thing here is that in our AIMD simulation, once it becomes a formate, it never go back. So that means that here the water gas shift reaction does not shift, and instead they will produce formate. And also this formic acid will dissociate. For example, this one we calculate the acid dissociation constant. And you can see that this constant increase with pressure, so that means that it dissociates more. But then if you increase temperature, for example, here that from 1000 Kelvin to 1400 Kelvin, and then that it dissociates less. The key reason here is that at a constant pressure, if you increase temperature here, the water dilation constant decrease. So that means that the acid will dissociate less here. Okay, let's go back to the key topic here. So in principle, water gas should shift, but now here does not shift here. Okay, one possible reason is that someone may argue that, okay, it's because your AMD simulation is too short. Okay, you have sampling bias here. Okay, then that to solve these problems that we perform the free energy calculation here. So basically we calculate first the change of enthalpy here. Okay, in this plot as a function of pressure and the two temperatures. And you can see that the enthalpy will decrease with increasing pressure. So that means that the reaction enthalpy becomes more negative and with increasing the pressure here. But the interesting thing is that if we further add the entropy terms into it, sorry. Okay. If you have any questions, please just interrupt me. It's fine. Okay. I'm happy to answer any of them. Okay, right. So if we add entropy term into it, and then we found that this the Gibbs free energy curve also has very similar shape as the enthalpy term. So that means that the entropy terms here does not change too much. So that means that the formic acid becomes thermodynamically more stable than the mixture of the CO2 and the hydrogen gas. So basically, that means that these reactions becomes like enthalpy-driven reactions. So the entropy here doesn't plays a very important role. So this is why that here you can see that from this plot, we found that indeed the formic acid is thermodynamically more stable than this mixture. So that means that our AMD simulations show you that it have these reactions, and it's not because that it don't have a very good sampling. It's simply because that the free energy prefer the formic acid here. Okay, that is also another interesting part that in the deep earth. Okay, so if that's
May I have questions?
yes, yeah, please.
Sorry to interrupt. Yeah, so you found that the enthalpy change between two solutions are very big. So it means that the PV terms is very different, or the electronic energy is very different.
I would say that here's both. I would say like this. So basically, like both that the energy and also the PV terms change a lot here. I would say that. But for the detail, which one change more? So sorry that I cannot remember clearly. But it's included in the supporting information of this paper, I think. Yeah.
Yeah. Thank you very much.
Okay, you're welcome. Right, right. So now the question here is that if the water gas shift reaction like this, and then how about like the Fischer-Tropsch type reactions here? And also that another interesting part is that, okay, now if you form this formic acid or formate here, and how that those things are important. Okay, so then that we found that, okay, this is basically a literature survey. We found that this formic acid or formate are very closely related to the diamond. Why? For example, like here, I just show a few papers, like our collaborators, Dmitry Svajinsky and his student Huang found that the diamond formations may be associated with a pH drop and from the destructions of formate. For example, that this is a reactant, and then finally it can become the diamond. And also that they found that in the formation of the diamond here, that they found that about 2.2 out of 13.8 moles of carbons in the diamond maybe is from this formate. Okay, like here. Okay, those are from the geochemical calculations. And also there are some indirect experimental evidence here. For example, that using the Raman spectroscopy measurements, Brazotti found that the surface of a natural diamond, okay, found here in Italy, are coated by functional group of carboxylic acid. So that means that it's like here. Okay, that is closely related to the formate. So that means that maybe this formation of a formate is related to the diamond, the formation of a diamond here. Okay, right. Okay, so now let's go back to this Fischer-Tropsch type synthesis here. Okay, so now before we just simulate just one carbon monoxide, So here, like if we increase the concentration of the CO here and also mixed with some hydrogen gas, basically make it more reducing. And then we compare these reactions with water and without water here. So first, we found that indeed, large hydrocarbons can be abatically synthesized through the CO polymerizations without any catalyst. Okay, so this is one part. Another part is that water plays an interesting role here. Okay, so this is another difference between this geochemical that Fischer-Tropsch synthesis and the industrial Fischer-Tropsch reaction here. It's because that in industry applications, basically there is no water, or strictly speaking, there is no liquid water. Yeah, it may produce some water, but it's just in the gas phase. But in the geochemical environment, so water is basically is almost everywhere here. Okay, so now here that basically like we calculate the difference with and without water. And for example, that we show here, so this plot just shows the carbon oxidation state. And so for example, this one is without water and this one with water at different pressure and temperature conditions. And generally, we found that water does not prevent the organic molecules formation, but restricts the product size reduction. So generally, we found that with water, and the product is a little more oxidized here. And also that, for example, like the hydrocarbons, the size here becomes a little bit small, but still we can have a lot of topic. It's called the orange of life. So it's all this because that as early as the 1970s, Charles Darwin has already proposed that the life could have emerged in a warm little pond with all sorts of salts, light, heat, and electricity. And later, this theory was further developed into this primordial soup theory, that is a geochemical theory of an abiotic orange of life. And as many of you probably also know this famous experiment called the Mino-Urey experiment to simulate the effect of light links to a mixture of simple gases. And they found the formation of many organic compounds, including the amino acid. Okay, so generally that for the orange of life, you can divide it into two types. One is that saying that, okay, the life is coming from the outer space. So for example, from like here, comets and or interstellar dust. And some argue that, okay, the orange life may come from the inside the Earth. So for example, that many of you propose that it's from the hydrothermal sources. Well, so hydrothermal sources, but some of your some scientists also argue that for these hydrothermal sources, because of the high temperature and many big molecules like proteins cannot be stable for a long time here. Okay, so here the general thing here is that okay, that orange of life usually is coming from some extreme conditions, not is from the ambient condition. So now, and because of that, and many studies are using the first principle calculation to study it. It's because that under such extreme conditions, it's usually very difficult to conduct experimental experiments. Okay, so for example, like let's just give two examples here. In fact, there are many others. And for example, like Gorman just applied AMD simulations and to basically to simulate the impact-induced shock compressions of cometary ices. And then that after they released the pressures to ambient conditions, the upper mantle, what will we have here? Okay, so here we conduct the AMD simulations. And then we found that, okay, basically, this is our, okay, one sample here. And we found a lot of organic products, I would say here. So for example, like overall that this CN or C2N species are the major component. And we found that with increasing temperature, and there are more like C2N species and fewer C2N2 species. And with increasing pressure, there are more like CN species. Okay, so there are many, I would say that at least 100 different types of organic products. And we found that in these simulations, we can have the glycine, and also we can have the ribose, and also we can have the uracil. But not exactly uracil. I will talk this later. It's like we call the uracil-like molecule here. Okay, to form those important organic bio-related molecules, and the key step here is that to form the carbon-nitrogen bond here. So that's why that we performed enhanced sampling simulations to calculate the free energy change to form this carbon-nitrogen bond. So it's shown in this plot here. So you can see that we compared three PD conditions, and the CO bond formation is always like it's always it's at the bottom of the valley here. But the interesting part here is that, for example, for these two conditions, it's metal stable state. Okay, so the system may prefer this state or this state. But for this red curve, so that is that at 10 gigapascal and 1400 Kelvin, we found that the carbon and nitrogen bond formation is favored. Okay, because this one is deeper than this one here. Okay, so then after we have this one, and then that we try to see whether we can form the glycines here. So then, similar to some previous studies, we found that it's easier to form these so-called hydroxyglycines from formamide here. And then that what we do is that we perform another additional simulations starting from this alpha hydroxyl glycine here, and then we make it mixed with hydrogen gas and water here, and then finally we see that we can have the directly have the glycine here. So that means that glycine indeed can be formed in our simulation here. And in fact, it's not only just the glycine. Another interesting part is that is the formation of the ribones in RNA here. Okay, so ribones is a very important component in RNA, and this is one segment of the RNA chain here. And the ribones is a type of sugar, and you can see it's here. So the interesting part is that you can see that we call it is a 5-member ring here. Okay, so like this one. But the interesting thing here is that we know at ambient conditions from the both experiment and also simulation, these simulations, for example, that we compare nations, why is that our life have this 5-member ring?